Okay, so this is homework 10.5, number 6B. If you saw the last video, we spent the whole first part of that video finding the final velocity of each of these carts. If you recall, we have one cart that's in motion that slams into a second cart, well, elastically, of course, and then that cart moves on to collide elastically with that third cart right there. So we drew this up as two separate collisions. Collision of 1 to 2. So this is cart 1 to 2 right here. And the collision of 2 to 3. Well, in part B right here, we need to find the momentum of the system before and after each collision. Or really, we want to verify that the momentum before each collision is equal to the momentum after each collision. So let's start just with the first collision of cart 1 to cart 2. You know what, you'd think I'd learn after last, I'm going to erase that and go up top here. For collision of 1 to 2, we're saying that the initial velocity of object 1 is called VO, okay, and the initial velocity of object 2, of cart 2, is 0 meters per second because it's not moving, okay? So we want to confirm momentum in part B before and after each collision. So let's simply write out the equation for momentum for all the parts of collision 1 to 2. That's like saying the mass of 1 times the initial velocity of 1 plus the mass of 2 times the initial velocity of 2 is equal to the mass of 1 times the final velocity of 1 plus the mass of 2 times the final velocity of 2. Okay, we're setting them equal to each other. And we want to see if this momentum right here, the initial momentum, is equal to the final momentum after that collision. So let's simply break these down into two separate parts. This is going to be part I for initial and part F for final. Okay, so initial. So we're going to find what the momentum was before the collision. M1 V1 or VI1 plus M2 initial velocity of 2. Well, this will become considerably easy for us because part of this is going to go away very quickly. What's the mass of cart 1? That's 4m, right? And what's the initial velocity of cart 1? We said that was called VO plus the mass of cart 2. That's 2m times the initial velocity of cart 2. Well, it's stationary, right? So that's 0. So that whole thing right there, that whole second part simply goes away. So the initial momentum of for collision 1 to 2 equals 4 times 4m times VO. Let me cancel that. 4m times VO. Okay, I'm going to put a dotted line box around that. And let's find now the final velocity. Final velocity, or not final velocity, the final momentum, I'm sorry, of collision 1 to 2. That's like saying, or that is saying, m1 mass 1 times the final velocity of 1 plus mass 2 times the final velocity of 2. Okay, we're going to see, and hopefully this is going to be equal to the momentum initial before the collision. because it should be. Okay, so mass 1 right here. What is that? That's 4m once again, right? What's the final velocity of cart 1? Well, I don't have it written here. In fact, I probably should have done that. But if you look back on your previous section, that is part A, finding the final speed of each cart, we said that the final velocity of cart 1 in the first collision is 0.33. I'm putting it in decimal form, not fraction form. VO. Okay. Very good. Plus what? Plus mass of 2. That's 2m. We're continuing this equation up above here. Times the final velocity of cart 2 in that first collision. And again, if you need to look back, you may have it on the same sheet of paper. I have it on a different one. But what's the final velocity of cart 2 in that first collision? That looks like it's 1.33 VO. Okay? So if we take that, if we multiply 4 times 0.33 and add it to 2 times 1.33, we actually get a final momentum from collision 1 of 4m times VO. Again, I realize it's a little bit abstract in that we don't actually have momentum, but we have a bunch of variables here, but we can see that this momentum is equal to that momentum. Momentum is conserved before and after collision 1, 2. Well, let's continue with for collision 2 to 3. Okay. We're going to see if momentum is conserved here as well. That's the job, to prove it, to verify it. The momentum of the whole system is conserved. Well, it's like saying the mass of 2 times the initial velocity of 2 in that second collision, plus the mass of 3 times the initial velocity of 3 equals the mass of 2 times the final velocity of 2 plus the mass of 3 times the final velocity of 3. Right now we can save some space and some time if we look at this. Remember, the final the initial velocity of cart 3 right here is 0. It's simply sitting stationary. So that means that this right here, the initial velocity of 3, that's going to be 0. So that's going to go away, and we'll just save ourselves some headache right off the bat. Okay, everything else is an actual integer, so let's plug in here. I'm sorry, we can't just yet. We want to solve these individually. Remember, this is our initial, and this is our final right here, so let's label it as such. So let's find our initial momentum, like we wrote it just above. INITIAL. Our initial momentum, that is simply this right here. That's m2 times the initial velocity of 2, which equals mass of 2 is 2m times the initial velocity of 2. Okay, here's where we had to think about this for a second. Remember, the initial velocity in that second collision for cart 2 is the exact same thing as the final velocity for the first collision. So if you need to go back and find out what that velocity is, what is it? That should be 1.33 VO. 1.33 times VO. Okay, and that comes out to 2.66 MVO. So that's our initial momentum before that second collision right there. Okay, let's see if the final momentum is the same, and if it is, we can check B off our list because we've confirmed it. So let's go ahead and do that. Final momentum. Well, that's the second part right here. Okay, and that, I'm gonna need this paper again. That is going to be m2 times the final velocity of 2 plus m3 times the final velocity of 3, which becomes m2 is 2m times the final velocity of 2 in that second collision. So what is the final velocity of 2 in that second collision? That looks like that is, we said it was 0.439 VO plus, what's the mass of 3? That's just m, right? Just regular old m times a final velocity of 3 in that second collision. That turns out to be 1.77 VO. Okay, so let's just do the math. Let's multiply 2m times 0.439 VO and add that 1.77 m VO. And if we do, we should get, well, I get 2.6, actually around 2.65 VO. I think the reason it does that because I took fractions and made them into decimals and rounded a little bit here and here in the previous problem. But this is reasonably close enough. 2.65, 2.66, very close, off by 100th. Okay, well, we can chalk that up to simply rounding, and we can say those are the same as well. Same. Momentum is conserved after each collision. Same. So we've done that. We've verified it. Verified that momentum of the whole system is conserved. So if you stuck with me through that, great job. Final thing is to verify the conservation of kinetic energy, and we'll do that in the final video, which will just be up in just a second. See you then.